Okay, now let's start looking at how we can use Maxwell's equations. And of course, the first thing we're going to try to do is to try to simplify them. And so our topic going into this discussion is electrostatics. Okay, so we've been looking at Maxwell's equations and associated boundary conditions. And so theoretically, we have all the tools we need to solve any in-end problem. But, in practice, the solution to Maxwell's equations end up being pretty complicated for sort of a generic scenario. Um, and so it's a very complicated solution. So it's not that easy to use Maxwell's equations. Of course, we can use it in plane wave, a lot of very useful applications, but in any average everyday application, it's kind of difficult to use to solve these four equations. Now, fortunately, there's some very practical situations where things are not time varying or they're varying at low enough frequency that we can pretend like things are not time varying. And therefore, the name in this particular case, electrostatics, meaning that the electrons are static or non-moving. And so that really simplifies, basically gets rid of the time varying version sections of Maxwell's equation, makes things a lot easier. Um, so let's see. So typically, in a static field, so look at it. You end up with when we solve. So these are basically kind of a couple of equations come out of this. They're called Laplace's and Poisson's equations. So typically what you have is when you look at a charge density, that gives you the sort of the electric flux, which is a vector, and then that gives you the electric field, which is also a vector. Now, if we look at the magnetic part of things, so we have from Maxwell's equation, we have del cross H is equal to the current density plus the change in the electric flux. But we're claiming that this guy, it's static, so it's not a function of time in these particular problems, not a function of time for electrostatic problems. So basically, if this change in d with time goes to zero, and then the current density J is current over area, and if charges aren't moving, then we won't have any current and no current density. So this also goes to zero. So it ends up that the curl of H ends up being zero. And therefore, um, there's no magnetic field because there's no current. And so this also makes B equal to zero. And also, of course, B equals zero means dB dt is equal to also zero. So this ends up going back to Maxwell's equation, means the curl of E, the function of R. If you remember, this was equal to minus dB dt. This ends up being equal to zero. So basically, we end up with a couple of things. So for all of electrostatics, so for all electrostatics, instead of needing all four of Maxwell's equations, we just need to solve two equations. First one is the one we just wrote. Del to curl of E is zero, and the other one is the divergence of the electric flux is equal to the charge density function of R. So, and then because, there's no changing magnetic field and there's no magnetic field period, we can say here that the electric and magnetic fields are decoupled. All right. Okay, so it seems like we're in good shape because if we have, again, if you have the charge density, from there we can get the electric flux, we can get the electric field from there. So we're good to go. But the problem is in most cases, so in most applications, it's very hard to measure charge density. So for example, imagine you're in the lab and you're trying to figure out what's going on with your capacitive circuit. It's really hard to measure charge density directly. So this business of starting with the charge density and moving from there to the electric flux to the electric field is not usually not practical either. Fortunately, we have a solution that presents itself, and that's because of a fact. I'm not going to show this, but if del cross E of R is equal to zero, okay, if this is a situation, which is it is in electrostatics, then we can come up with a another quantity called potential or voltage. So in fact, this voltage is potential is what we typically start use as a starting point in the lab because we have easy ways of measuring the voltage on a node, the potential on a node. So in fact, what you do is in a typical problem in lab, you measure voltage, potential. From there, you get the E field, and from there, you get the D field, and from there, you get the charge density. That's what you typically end up doing. So, okay, okay, great. So we have this potential, but how do we come up with the potential? So it turns out, yeah, and I'm not gonna show it to you, this to you guys, but it turns out oops, from vector math, if we have this situation, then we can define something called basically we can define, so this is not just for the electric field, but anytime you have a vector field where the curl of the vector field is equal to zero, then you can define the vector field as the gradient of a scalar field. In this case, we call that V or potential. So if curl of vector field is zero, we can define vector field as gradient of scalar field. So the definition of potential for electric potential, and we call it voltage, is amount of work done on a charge in moving it from point B to point A. So that is equal to minus B to A E dot dl. So let's say you have electric fields. Let's say the electric field is defined in this direction. You have electric fields going like that. And then we have a charge at a location B, and then we want to take that charge to location A. And let's say we took a funky route to get there. At any point, we pick the this line segment, very tiny line segment, DL, and then we figure out the dot product of that direction with the direction of the force. So the work is defined as the small the um, the tiny bit of work required to take this across this small segment, and you sum all the works together across all the DLs to get from B to A, however way you get there. Okay, so dW is equal to minus F dot dl. This minus here is because we are finding work done on the charge. And force is related to the electric field by multiplying the unit charge by the electric field. Because there's no magnetic field, it's just simply QE. And so this is minus QE dl. So the total work to get from B to A over Q is BAB is minus B to A E dot dl. And so this is the starting point of what is called Laplace's equation. Is E is the gradient of V. Okay, so now let's look at a case. Let's look at a surface where and assume no charges inside. So assume no charges inside the surface. So this is a region with associated surface S and associated volume V. So Gauss's law says that del dot D here, it usually would be equal to the charge density, but because we're saying there's no charges inside, it just would be equal to zero. So, and then D is equal to epsilon electric field. So del dot E is also equal to zero. And E is just equal to minus del V. So E is minus del V. So basically putting these two together, we end up with the gradient of, sorry, the divergence of the gradient of V is equal to zero. And so the divergence of the gradient, we give it this symbol squared, and we call that the Laplacian. And so the Laplace's equation is just del squared of V is equal to zero. And the so that's Laplace's equation. In rectangular, only in rectangular coordinates, this Laplacian is equal to the double derivative in the double partial derivative in all directions. So remember, this is only in the rectangular coordinates. In spherical and cylindrical coordinates, I guess it ends up being a fairly complicated relationship. Okay, so if we just take this, we end up with del dot D is equal to charge density. So del dot E is charge. So now there is a charge density, say, or there's a possibility of a charge density. And so del dot V is minus rho V over epsilon, and the Laplacian of the voltage, which is a scalar field, so it's a function of position, is minus the charge density, which is also a scalar field over epsilon. And this ends up being called Poisson's equation. So it turns out, in a typical situation, it's a lot easier to solve these equations. So let's look at a situation where you have a charge plus Q inside a sphere. And so the sphere has, the sort of the unit surface vector on the sphere is ds. And then because this thing is at the center of the sphere, the electric field is radially going out all these places in the sphere. And the surface ds um, just in cylindrical coordinates ends up being r squared. Sorry, not cylindrical coordinates. This is in spherical coordinates. Is r squared sine of theta d theta d phi, and and then also E is equal to E sub R of R. The reason for the sub R is in this case because the unit charge is at the center of the sphere, the E field only has oops, radial component. Okay, so we do the Gauss's law thing, which is we integrate over the closed surface E dot the ds, and that's equal to the total charge inside, which is plus q over epsilon. And since we took the simple case of this being a sphere, our integral ends up being very easy. It ends up being E sub r 4 pi r squared, which is the surface of the sphere, is q over epsilon, and E sub r is q over 4 pi epsilon r squared. Now, on the sphere, potential on the sphere is V sub A is the work that it took to bring this test charge we're going to bring from infinity to the point A, which is on the surface. So A is any point on the surface over the electric field 4 pi epsilon r squared r dot r dr. So this is the field in radial direction, and this is the path in the radial direction. So because if you think of anything coming from infinity to our sphere, the path has to be kind of just radially coming in radial direction. And let's say we define this is pretty typical, the voltage at infinity to be equal to zero. Okay, in that case, we end up with V sub A is Q over 4 pi epsilon R. Okay, let's see. So, um, again, in general, so what people do is to solve these problems, to solve these kind of problems, to solve electrostatic problems. What people do is they use Gauss's law and symmetry, and good knowledge of integral math to solve these problems, to solve electrostatic problems. I guess I mean, this is the part where I'm assuming the rest of you guys, like very few people are good at that, but fortunately there's some good examples of that. So one thing So that's sort of laying out electrostatics for you. And then the next lecture, we're going to be talking about um, some examples of how to solve some typical problems with electrostatics. A couple of examples. Just wanted to leave you guys with one very important thing, which comes out of the equations, which you guys want to be very careful about this. Careful that or just you have to remember that because of this relationship, that E is minus divergence of V, that the electric field is always perpendicular to lines of constant potential, okay, which is the definition of a gradient function. So just wanted to remind you again, it comes with the math, but just a reminder that this is always the case, is when you have lines of equal potential, the electric field is always pointing vertically to those equal potential lines.